Hello and welcome to Lecture 2. Today we'll be talking about formal definition of a derivative. Now, I've written it down here already, and basically, so let me get a little closer, this definition and this concept was groundbreaking. It was discovered simultaneously by Leibniz and Isaac Newton, and both of them lay claim to it. I believe Newton's treatise on the derivative is more complete and interesting. However, Leibniz does create some very interesting notation, and his discussion of integrals is paramount. So, both thinkers respected their field, and should be so. Okay, well anyway. Alright, so we have this limit, and it's h goes to 0. So, this is an infinitesimally small change. And basically that's what derivatives are. They're looking at infinitesimally small changes. Very, 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 very tiny. So like, you can't even actually think about it because it's just conceptual. So, it's sort of poetic in a way. I would think about it kind of like, I don't know, a speck of dust in the air. I mean, that would be how small this change is, like the length of that speck. So if you have like, a speck like this, the length of this, the length L, which you can't even really write, you can't even really see it, it's so small. Okay, so this speck, and that's basically the length of this change, to give you an idea. Okay. So now that we've been ridiculous and silly, let's do an example problem. So the limit of h goes to 0, and we'll just take x squared. Okay, and this is going to equal an f of x. And this is our function. Alright, so let's talk about this for a second before we start into our problem. So if you have something like this, and that means at all values, you basically view this x like a parentheses. That's how I do it anyway. So, and inside the parentheses you write x plus h, and then you close the parentheses, and then you do the function's rule or operation. So another example of this will follow, and we'll just think about parentheses. Okay? So we have x plus h squared minus x squared over h. And now what we're going to do is we're going to FOIL this guy out. We get x squared plus 2xh plus h squared. And that should be pretty clear how I did that. Right? Because okay. Oh, excuse me. Alright, so now we're going to plug this result into here, because this is equivalent to this. So we have limit h goes to 0 of x squared plus 2xh plus h squared minus x squared over h. Okay, and now we're going to do our cancellation, so those go away, and we're left with the limit, so h goes to 0, oh, and also we're going to cancel these off, right, so 2x plus h, and plug in 0 and we just get 2x. So we've essentially seen the formal definition of a limit, and now we're just going to work through some examples with f of x plus h for some other things that you might encounter. So another one would be like, so we have x, f of x equal e to the x. So where you see this x, you're just going to put a parenthesis, so this is going to be x plus h. Now it seems pretty easy, but it can get complicated. So like, let's say f of x equals x cubed plus x squared plus x plus 3x squared, and then, I don't know, plus x to the 7th. Now, functions of this form, it's going to get a little confusing so you really want to drive home this concept. So, now obviously there's nothing to work out here. You just have to literally go through. And just plug and chug. Alright, so I'm going to view that across. Alright. And the second sweep, and this is x plus h to the 7th. I'm sorry, it didn't come through very clearly. Alright. So this is the formal definition of a derivative. This is how you calculate it. Next time we'll go through the easy way of calculating a derivative, but you should work through some examples like this. Just come up with some numbers and plug away.